Hello students, today I am going to start a new topic, that is alpha decay. Alpha decay is one of the most common mode of radioactive decay. So by emitting an alpha particle, a nuclei in the higher excited state, it can lose energy. The nuclei which is in higher energy state and it is unstable, it can emit alpha particle and it can convert into a more stable deuter nuclei. It can convert into most stable deuter nuclei. What is alpha particle? You are all aware about this. This is helium nuclei. 2He4 nuclei is known as alpha particle. So first question arises about alpha decay is when alpha particle is emitted by a nuclei, then how can we calculate the kinetic energy of this emitted alpha particle? How can we calculate the energy of this alpha particle which is emitted by the nuclei? So for this, basically magnetic spectrometers are used and these alpha particles are passed through the magnetic field, and under the influence of magnetic field, a magnetic force QV cross B force will be exerted on this alpha particle, and as a result of this force, this particle will trace a curvature. It will take a curvature, and with the help of the measurement of the curvature, radius of curvature of this curve, one can find out the kinetic energy of the emitted alpha particle. So basically, this alpha decay is one of the primary modes of radioactive decay. Other modes are beta decay and gamma decay. But in general, this alpha decay is common in heavy nuclei for A greater than 150. So alpha decay is most common is most common in heavy nuclei. Common in heavy nuclei. Having a number greater than 150. Having a number greater than 50. So basically, heavy nuclei whose A number is greater than 150, if they are having excessive energy, they can lose their excessive energy by emitting alpha particle. Okay? Alpha particle, what is alpha particle? Alpha particle is the helium nuclei. If you want to write down a general equation for the alpha decay process, then it can be written as, suppose this is the parent nuclei ZXA. It will convert into another nuclei Y by emitting an alpha particle, that is 2He4. And what will be the Z number here? 2 is here Z. So this will be Z minus 2 and this is A minus 4. So this is the general equation, and here energy will be emitted, and that energy will be in the form of kinetic energy of alpha particle, and a small amount of kinetic energy will be carried by this deuter nuclei, Y nuclei. So this is the general equation of alpha decay. Now first question is, how can we measure the kinetic energy of this alpha particle? So kinetic energy carried by alpha particle. So basically this problem can be sorted out, or this kinetic energy can be measured with the help of magnetic spectrometers. So with the help of magnetic spectrometers, we can measure the kinetic energy carried by these alpha particles. When this alpha particle is passing through the magnetic field, it will experience a force QVB. V is the externally applied field. B is the externally applied field, Q is the charge on the alpha particle, V is the velocity of the alpha particle. Here even you can write this is Q alpha, this is V alpha, and this B. So when this alpha particle is passing through the magnetic field, this force will be experienced by the alpha particle, and under the influence of this force, this alpha particle will take an curvature. For the curvature, when it will try to move in a circle or in a curvature, then it will experience basically centripetal force. And what is the formula for centripetal force? This is m alpha v alpha square mv square upon r. This will be r. So basically, for traveling a particle on a curvature, on a curved path, it needs a centripetal force. And from where this centripetal force is coming into the picture, this centripetal force is provided by this magnetic force, Q alpha, V alpha into B. Now, from here, what can we find out? We can find out that M alpha, V alpha is equal to Q alpha, this B, and this R, radius of curvature. This will be. Now, what will be the kinetic energy? Kinetic energy of alpha particle is suppose K alpha. Then this will be 1 by 2 M alpha V alpha square. We can replace this by M alpha V alpha square. So 1 M alpha is higher, here is extra. So here we will multiply this denominator by M alpha. Now substitute this value of M alpha here. So this will be this M alpha V alpha will be replaced by Q alpha B into R. So this kinetic energy K alpha will be equal to Q alpha square B square into R square divided by 2M alpha. So this is the formula for the kinetic energy carried by the alpha particle. So this much amount of kinetic energy will be carried by this emitted alpha particle. Here we can take an example. Here this is the kinetic energy. So when this alpha particle will be emitted, so much kinetic energy will be carried by the alpha particle. When alpha particle is emitted, then in this reaction, some energy is released. And this energy Q alpha will be in the form of the kinetic energy of this Y deuter nuclei and this alpha particle. Now what will be the value of this alpha particle? So if we take the example of the alpha decay of 92 uranium-238, or here in general, if you want to find out the Q alpha, what will be the expression of Q alpha? First I am writing a general expression. What will be the value of Q alpha here? This will be equal to the mass of the parent nuclei. What is the formula for Q? Q value of a reaction. This is mass of the parent nuclei minus mass of the daughter nuclei. So what is the mass of the parent nuclei? This is mass of X nuclei. This X nuclei minus mass of the daughter nuclei. This is Y minus M alpha into C square. Here these masses will be in kg. Here these are the masses of these nuclei X, Y and alpha particle, but these masses are in kilograms. So if we multiply this by C square, then we will get Q alpha in terms of joules. So here we will find out our answer in joules. But here these masses, you have to remember that these masses are in kilogram. Suppose we want to find out this Q alpha in MeV, and these M alpha, Mx, My, these masses, they are given in AMU, atomic mass units. Then this will be the equation. We will multiply it by 931.5. Here these masses, they are given in AMU, so it will be in MeV. Now this Q alpha, we can find out this Q alpha in terms of MeV. Now we want to find out the estimate of this Q alpha. What will be Q alpha in general? So for this, we can take an example of 92 uranium 238. So this will be 92. So here we are taking an example of 92 uranium 238. So it will emit an alpha particle and it will convert into 90 thorium 234 plus 2He4. 2He4. So what will be the Q value of this alpha emission process? This will be mass of uranium minus mass of the daughter nuclei thorium minus M alpha. And if these masses are in AMU, then we will multiply this by 931.5 and answer will be in MeV. Now what are the values of Mu? Masses of uranium 238, uranium 234, helium 4. So if we substitute these masses here, I'm going to substitute here masses. So I don't remember, but you can write mass of uranium is 238.050770770. This is in AMU. This is the mass of uranium minus mass of the thorium is 234.043583. This is the mass of thorium minus the mass of helium nuclei. This is 4.002604 in AMU. All these three masses are in AMU. Multiply this by 931.5 and your answer will be equal to 4.269 MeV. So this will be the Q value for this alpha decay of 92 uranium 238. So when this nuclei, radioactive nuclei 92 uranium 238, it undergoes alpha decay, then Q alpha of this reaction comes out to be 4.269 MeV. Now question arises, why this alpha particle decay is so common? Why this alpha particle decay is so common? So basically alpha particle, if you consider why alpha particle decay is so common, I just want to make you a heuristic picture. I want to answer this question in a heuristic way. So this alpha nuclei, 2He4 nuclei, this 2He4 nuclei, this consists of 2 protons plus 2 neutrons. 2 protons plus 2 neutrons. So when an alpha particle, basically you can say if this is the nuclei, this is any nuclei, and this alpha particle is coming out of it, it means 2 protons plus 2 neutrons, they are coming out. So when alpha, for the emission of alpha particle, what is needed? We want to remove 4 nucleons from the nuclei. And this will be a heavy nuclei. This will be heavy nuclei. For heavy nuclei, binding energy per nucleon here, I'm writing binding energy per nucleon is nearly equal to, you can say this is 7.0 MeV. This is nearly 7.0 MeV. And here we have 4 nucleons. So how much energy is needed? So energy needed to remove alpha particle from nuclei from nuclei is nearly equal to, I will say nearly equal to 7 into 4. For one nucleon, for the removal of one nucleon, we need 7 MeV of energy. So for 4 nucleons, roughly we will need 28 MeV. 28 MeV energy is needed. And later on, in this discussion of alpha decay, we will find out then that this alpha nuclei doesn't pre-exist. This alpha nuclei doesn't pre-exist inside the nuclei, rather it is formed. This alpha nuclei, this alpha particle or this helium nuclei is formed only at the time of the emission. So at the time of emission, this alpha nuclei, alpha particle is created inside the nuclei. So correspondingly, when this alpha particle is created, then some energy will be released. And from the discussion of the binding energy, we are aware that when binding, basically when alpha particle is created, then what is the binding energy of the helium nuclei? Means energy released, binding energy of this helium nuclei, or when this nuclei is formed, how much energy is released? That is greater than 28 MeV. 28 MeV. That is greater than 28 MeV. So when this alpha nuclei will be formed at the time of emission, so much energy is released, which is greater than 28. And the energy required by this alpha particle to move out of this nuclei is roughly 28. So this energy for the removal of these 4 nucleons or the alpha particle from the nuclei will be provided here when this alpha nuclei is formed. So due to this reason, this alpha decay is one of the common mode by which nuclei in the excited state can lose its energy. Now, I'm saying another aspect. I'm saying that this is a common mode in A greater than 150. It is most common mode in the nuclei having A number greater than 150. Experimentally, how we decide this number? How we decided this number experimentally? This is very simple. If you plot this Q alpha as a function of A, if we plot Q alpha as a function of A, so here on this axis we have Q alpha in MeV, and here we have A number. So on the x-axis we have A number. So we have here 50. I'm writing this is 100, 150, 200, and this is 250. And roughly this is 300. On the y-axis we have Q alpha. Suppose this is minus 10. Then this will be minus 5. This will be 0. This will be plus 5. This will be plus 10. This will be plus 10 or 15. We can go up to 15. Now we draw a horizontal line here corresponding to Q alpha 0. Now plot Q alpha for different nuclei. So if we take different nuclei, then corresponding to this different nuclei on heavier side, if we take different nuclei here and we consider this type of equation and calculate this Q alpha. So what we have to do? We have to take here different nuclei having different values of A and just write this type of equation and calculate the Q alpha value and plot that Q alpha value as a function of A. Then you will find out this type of equation. you are going to find out this type of equation. You are going to find out this type of equation or plot. Not equation, this will be a plot like this. You are going to find out this type of plot. So from here, you can observe that up to a number roughly 150, up to 150, this Q value is negative. Up to in this regime, Q value of this alpha decay is less than 0, and here this Q value is greater than 0. So in this region, if you want that a particular nuclei having a number less than 150, it emit an alpha particle, then we have to provide some external energy to the nuclei because this Q alpha is 0. So we have to provide some external energy to the nuclei so that alpha particle emission can take place. But here, on this side, for a greater than 150, this Q alpha is 0. So this will be a naturally occurring process. And in this process, we will not provide some external energy. Rather, when alpha particle will be emitted, some energy will be released. So that's why we have written that it is one of the most common mode in heavy nuclei for a greater than 150. Another important aspect that was known about these alpha particle was given by Giger and Nuttall. There were two scientists, Giger and Nuttall. They gave a law. On the basis of experiment, they find out an equation, and that equation, linear equation, is known as Giger-Nuttall law. So another is Giger-Nuttall law. Giger-Nuttall law. What information? This can have various shapes. You will find out different linear equations. It will have different forms. So one of these is log T half. Log T half is equal to A plus, this will be B. A plus B Z upon square root of Q alpha. Here A and B are constant. Z is the charge number of the nuclei, and this Q alpha is the Q value of the alpha decay process, and T half is the half-life of the nuclei for alpha decay process. So they find out this type of relation. And value of A is minus 52, roughly minus 52.81. This was equal to minus 52.81, and this B was 136.1. This was 136.1 upon 84. Here you have to remember that this T half is in seconds. This T half is in seconds, and this Q alpha is in MeV. So you have to remember that this T half is in seconds, and this Q alpha is in MeV. Directly you can substitute these. So this equation is known as Giger-Nuttall law. This is known as Giger-Nuttall law. This was the equation. This was for this was for even nuclei. They find out this type of relation for even nuclei. They observe this type of relation for even nuclei. So this type of relation was found out by Giger and Nuttall experimentally. This is an important relation when we will find out, or when we will develop the physical process or some phenomena with the help of which they will explain. We are going to explain this alpha decay process. Then finally we will show that we are also getting this expression correctly. whatever expression we are finding out, that is matching with this one. So this will be a confirmatory test for the theory that will be developed for alpha decay. So this is one of the important laws which was found out experimentally by Zeeser and Nuttall. Now, next question arises, how this alpha particle comes out of the nuclei physically. What is the physical phenomena that is happening due to which this alpha particle is able to come out of the nuclei? And we want some mathematical background also. So this mathematical analysis as well as physical reasoning was provided by Gamos. There was a scientist, he provided Gamos' theory of alpha decay, and on the basis of this, he find out the expression of lambda probability density, basically decay probability. He find out the expression of decay probability on the basis of a physical phenomena that is known as quantum tunneling. Now, first question is, what are the postulates which were made by Gamos, or on the basis of which postulates this Gamos theory was based? So first and foremost postulate was this alpha particle. This alpha particle doesn't pre-exist, does not pre-exist inside the nuclei. Inside the nuclei. This was one of the foremost and one of the most important postulate that was given, that was assumed by Gamos. So basically he was saying this alpha particle which is emitted by the nuclei, this doesn't exist inside the nuclei. It doesn't pre-exist inside the nuclei. Rather, it is formed. This alpha particle is formed at the time of emission. So what is happening inside the nuclei? Two protons and two neutrons, they are coming together at the same time at one place, and alpha particle formation is taking place. Now this alpha particle will try to come out of the nuclei, and if that is not possible, then it will disintegrate. Again alpha particle will form, it will try to move out of the nuclei. If it doesn't get success, again it will disintegrate. So this process of formation and disintegration will continue up to the point when alpha particle moves out of the nuclei. So this was the first and foremost assumption made by the Gamos. Second important assumption that was made by Gamos was that alpha particles in negative energy states. Negative energy states means bound state. Cannot move out of the nuclei. What he was saying, that only alpha particles having positive energy may overcome the Coulomb barrier and come out of the nuclei. of the nuclei. These are the two postulates which were given by, or which were assumed by Gamow. His theory was based on these two assumptions. So, first question is, how much Coulomb barrier potential is faced by this alpha particle? So, alpha particle has to cross the Coulomb barrier. What is the numerical value of this Coulomb barrier? The estimate of this Coulomb barrier can be easily made. Here, this is the radius, this is the center of the nuclei, and this is the radius of the nuclei. And here, this is the height of this Coulomb barrier. This is the how, and alpha particle have to come out of this nuclei, come out of this Coulomb barrier. Energy of the alpha particle is Q alpha, which is positive. This is also the energy of the alpha particle possessed by alpha particle. And this alpha particle have to cross this Coulomb barrier, which is here. How? What is the expression for Coulomb barrier? Basically, Coulomb barrier is always there when two charged particles are interacting with each other. What is the expression of Coulomb potential? That is U is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R. This is the expression you are aware from your class 12. So now here, how can we estimate this Coulomb barrier B? Coulomb barrier. This is the maximum value. This B is the maximum value of this Coulomb barrier. And after this R, this is going to decrease as 1 by R. U is proportional to 1 by R. So it is going to decrease. So first question is, how we will calculate this maximum value of this Coulomb barrier B? So basically, we will estimate this value of B at the point when deuter nuclei and alpha particle, they are just going to move away from each other. Here they are touching each other. They are just a moment away when they will be separated out. So when they are going to be separated, at that moment we can easily calculate this barrier potential. What will be the charge on this deuter nuclei? What will be the charge on this deuter nuclei? That will be Z minus 2E. This will be the positive charge that will be carried by this deuter nuclei. Here deuter nuclei is Z minus 2, Y, A minus 4. What will be the charge on this alpha particle plus 2E? And when they are just going to be separate out, what will be the radius? This radius will be center to center separation will be the radius between them. What is the value of this R? How can you calculate the radius? Here you can use the formula for radius. And what is the formula for radius? This will be equal to, R will be equal to radius of deuter nuclei plus radius of the alpha particle. So what will the center to center separation? This will be, suppose R, this will be for deuter nuclei, radius for deuter nuclei plus radius. So what will be RD? This will be R naught. It will be AD. A number for deuter nuclei divided by 1 by 3 plus, what is the A number for this? For alpha particle, this will be A alpha to the power 1 by 3. Where R naught is a constant, you are aware, and R naught is nearly equal to 1.2 Fermi. We have already discussed these things. So this is the expression of R. So when this deuter nuclei, when the center of deuter nuclei and center of this alpha particle is at a capital R distance away, at that point we can calculate this Coulomb barrier potential. So what will be the Coulomb barrier potential? It will be ECR, and this will be equal to B. And its value will be how much? This will be 1 upon 4 pi epsilon naught. Multiply Q1 and Q2. Q1 is this, Q2 is this. So this will be Z minus 2 into 2E square upon R. So this is the formula. This is the formula for the Coulomb barrier potential, maximum value of barrier potential. This is the maximum value of barrier potential. This is the, so alpha particle has to cross this. Alpha particle has to cross this Coulomb barrier potential. As the separation between alpha and deuter nuclei, as the separation between the deuter nuclei and this alpha particle is increasing, then automatically this Coulomb potential is going to decrease, because this will be proportional to 1 by r. Separation between this deuter nuclei, separation between the center of deuter nuclei and this alpha particle. So because it is 1 by r, so in this region it will go as 1 by r. This type of variation for the Coulomb barrier potential it is going to be. Now here, the energy, the positive energy, total energy that is positive, that is possessed by the alpha particle, this is E alpha. This E alpha is the total energy that is possessed by this alpha particle. This is equal to Q alpha. And here this energy is less than B. Here this energy is less than B. Here this is Q alpha. And this is B. So this Q alpha is less than B. This Q alpha, which is roughly 4, which is roughly equal to 4. Basically, this energy Q alpha is 4 MeV, so this energy is less than this B barrier potential, Coulomb barrier potential. So classically this alpha particle whose energy is less than barrier potential, it cannot cross the barrier. Classically it is not possible. Classically, if energy of the particle is less than the barrier height, it cannot cross that barrier, particular barrier. But at this point, quantum mechanics came as a savior. According to quantum mechanics, it is possible. It is possible. If a particle having energy less as compared to a barrier, then there is a certain probability according to quantum tunneling phenomena. According to quantum tunneling phenomena, there is a certain probability. So, according to quantum tunneling phenomena, basically there is a certain probability that the particle having energy less than the barrier height can cross the barrier, and it is given by e to the power minus 2ka, where a is the barrier height. Here we are considering this barrier height is constant throughout the barrier, and this k is given by 2m, where k is square root of 2m. This will be Vc minus E upon h cross square. This is the formula for K, where A is the barrier width, and throughout the barrier, when this formula is used, basically throughout the barrier, we have this type of barrier. We have this formula is for this type of barrier, where height of the barrier is, suppose whatever is the height here, that is constant throughout the width of this barrier. This here, this is A. We are assuming this as A. And this barrier height is constant. This Vc is constant throughout. And E is the energy of the particle. So there is a certain very small, but certain probability that particle having energy less than the barrier height can tunnel through this barrier. Here in this case, if we consider, this is the formula for that probability. This will be very, very less. This is exponential minus 2ka. So this will be a small probability. Here, when we look at our barrier, then this is our barrier. Our barrier is like this. Our barrier is like this. Here, at this point, at this distance, when R becomes B, at R equal to B, basically energy of the alpha particle becomes exactly equal to the barrier potential. So, what is the width of the barrier? What is the width? First is, what is the width of the barrier here? What is the width of the barrier in our case? So, in our case, width of the barrier is equal to this B minus R. This B minus R. We have the formula for this R. We already have this formula for this R. But how will you calculate this B? How will you calculate this B? This formula is okay. This formula is okay. Width of the barrier. If you want to calculate the width of the barrier, then you will use B minus R. R you can calculate from here. How can you calculate this B? So look at this B. At this R equal to B, energy of the alpha particle, Q alpha, becomes equal to this Coulomb barrier height. So from where we are going to calculate this B, we are going to use this formula. So this Q alpha, at point B, energy is Q alpha. So this Q alpha or this E alpha, energy of alpha particle, this is equal to 1 upon 4 pi epsilon naught Z minus 2, and this will be 2E square upon this will be B. So by using this formula, we can find out the value of B, and in this way one can estimate the barrier width of the barrier. In exam sometimes they can ask you to calculate B, this capital B. They will provide you the value of A. If they are going to provide you value of A, you can calculate this capital R, so you can calculate this R. They will provide you Q alpha, so you can calculate this B. They will provide you these values. And if we divide these two equations, what we are going to find out, if we divide these two, this B divided by this Q alpha, if B divided by Q alpha, this will be equal to B upon R. This will be the formula. Out of these 4 quantities, they will provide you 3. They will provide you the means to calculate these 3 values out of these 4, and 4th you can calculate. So this is the important formula. This is another important formula on the basis of which they can ask some numerical question in the exam. This is another important formula. Now, if we consider this type of barrier potential here, this barrier height, this VC, it is constant throughout the width of the barrier. But here, in our case, this barrier height is decreasing. This is variable. Barrier height is a function of R. So in our case, this barrier height is a function of R. So probability of tunneling of this alpha particle out of this nuclei, it can be written as here, this formula for P, it will become equal to e to the power minus, it will be e to the power minus 2 times, it will be e to the power minus 2 times, and here we have to use integral, this will be kr and this will be dr. So if you want to find out the probability of this alpha particle through this barrier potential, then this will be the formula. If we solve this formula, substitute different values, then we find out finally what formula we are going to finally. we are going to find out log. This will be 10 to the base log 10 to the base p, and here it will be 1.42 square root of ZD. ZD is Z minus 2. ZD is Z minus 2. This is the Z number of daughter nuclei. A to the power 1 by 3. A to the power 1 by 3 minus 1.72 ZD divided by square root of Q alpha. Q alpha. On solving this equation by substituting this K and solving by using some mathematical method, one can find out this equation. One can find out this equation. So here this relation gives basically this equation provides us the relation between the probability of tunneling and this Q alpha value. We are somewhere close. By this equation, we are somewhere close to Ziegler-Nuttall law. Ziegler-Nuttall law. But what is our objective? We want to find out decay probability. But our objective is to find out decay probability. And decay probability is represented by lambda in case of alpha decay. This is also known as decay constant. In radioactivity chapter, you are aware about the decay constant. So decay constant is also known as decay probability. So we are interested in this alpha. In alpha decay process, this lambda will be made up of three terms. One will be P alpha. First term is P alpha. Second is F. And this third is P. Third is P. So here this lambda is made up of these three terms. What is the meaning of these three terms and how this lambda is constructed by the multiplication of these terms? Here, first term P alpha is probability of finding an alpha cluster inside a nuclei. P alpha, where P alpha is probability of finding the cluster of 2 proton plus 2 neutron inside the nuclei. From where we are getting this term P alpha? Basically, alpha particle is not pre-existing inside the nuclei. So if you want alpha decay, then first it is required that 2 protons and 2 neutrons, they combine together and they form alpha particle inside the nuclei. So for this, there will be some probability of the formation of the alpha particle by the clustering of these 4 nucleons. So that probability is P alpha. So this is the first part. First, what is required? Alpha particles should form inside the nuclei. After this, what will happen? When this alpha particle is formed inside the nuclei, suppose this is the nuclei here, this is R, this is also R, this is O, and these are the extreme. Basically, this is the diameter of the nuclei, and diameter will be equal to 2R. Here, this diameter will be equal to 2R. So what is going to happen inside the nuclei? When this alpha particle is formed inside the nuclei and it has some kinetic energy, this will have some energy. When alpha particle is formed inside the nuclei, it will have some energy, and due to this energy, it will move inside the nuclei. Suppose with energy V alpha. Suppose it is carrying energy V alpha. Suppose it is carrying some energy E alpha, and corresponding to that energy, it will move with some velocity V alpha. When it is moving with V alpha, then what is going? It is going to this side, it will strike this surface. Either it will move out or it will be reflected back. In that case, it will move in this direction. Again, it will strike the surface of the nuclei. Either it will pass or it will be reflected back. So in this way, this alpha particle will start oscillating to and fro. It will start, you can say this alpha particle will start striking the surface here and here, here and here. So there will be some collision frequency. So there should be some collision frequency, and this F represents the collision frequency. This F represents this collision frequency. So first this alpha particle is formed, then due to its energy, due to its kinetic energy, it starts striking the nuclear surface so that it can move out of the nuclei. So for this, we need a term that is known as collision frequency. This collision frequency, represents the number of times this alpha particle is striking on the nuclear surface in 1 second. In 1 second, how many times this alpha particle is striking on the surface? That is collision frequency. You can make a rough estimate of this F. What will be F? F will be 1 upon T. The time between two successive, this T is the time between two successive collision. What will be the time between two successive collision? This you can calculate this time. How much distance? First collision is suppose here, second will be here. So in between two collisions, how much distance it is traveling? That is 2r. With what velocity? This is V alpha. So this T will be equal to 2r divided by V alpha. So this is the formula for this collision frequency. This is the formula for the collision frequency. How can you estimate this V alpha? How can you estimate this V alpha? R we can calculate from here, but how you can calculate? This can easily be calculated. Total energy, from the total energy of the alpha particle, E alpha is equal to Q alpha. And this will be equal to kinetic energy of the alpha particle, half m alpha V alpha square, plus potential energy. Potential energy is minus V naught. Minus V naught. So with the help of this formula, one can estimate the V alpha. And in this way, you will find out this F. And third is P, the probability that alpha particle will cross the barrier. Probability P represents the probability that alpha particle will cross the barrier. So first, alpha particle is formed inside the nuclei. After this start oscillating, it is striking on the nuclear surface. And if we multiply this by the probability, out of so many collisions, suppose one time it will move out, then there will be a certain probability of coming out from the nuclei. It will have certain probability. That probability is P. If we multiply these three factors, then surely this will give us the decay probability or decay constant. So in this way, one can calculate decay constant or decay probability with the help of this. Now, if we substitute this value of P, if we substitute this value of P here, in this equation, if you substitute this value of P here, then you will find out a resultant equation. Then you will find out final equation. And this final equation, I'm going to write here. This will be log 10 to the base lambda. Is it visible? Yes, it is visible. This will be equal to log 10 to the base P alpha. P alpha plus 21.46 plus log 10 to the base. This will be square root of Q alpha plus V divided by a to the power 1 by 3. A to the power 1 by 3 plus 1.24, and this will be square root of, ZD a to the power 1 by 3 minus 1.72 ZD upon square root of Q alpha. This is the final equation. And this expression agrees with Ziesner-Nuttall law, in which most important or most dominant energy dependence comes out. So basically, more out of these four terms, the first, second, third, fourth, if you plot this, then you will find out that most important energy dependence comes out from this term. And it provides us the exact relation that was given by Ziesner-Nuttall. So log lambda is proportional to ZD upon square root of Q alpha. So in this way, with Gamow, with the help of his assumptions, he explained the decay of alpha particles with the help of this quantum tunneling effect. And he found out all the numerical values which were nearly matching with experimental values. This is all about the Gamow's theory.